two things we need to know about graphs of n against z for stable nuclei is that for small nuclei up to z equals about 20, the graph's a straight line, n equals z. But when the nucleus gets bigger, you need more neutrons than protons, so therefore the curve curves upwards. And for big nuclei, the number of neutrons is about 1.5 times the number of protons. So in this case, the graph goes up to 80 protons, so we'd expect to be going up to 120 neutrons. So it says do a scale, so bringing a ruler on here, you can very conveniently get a scale where 1 centimetre represents 10 neutrons, and fairly approximately the first part of the graph is a straight line, and then we're going to be going through about the point 80 across and 120 up. So the graph then curves like that. And the things they would check when they were marking it, that was a straight line up to 20, and that is about 120. Doesn't have to be bang on, but somewhere between 110 and 130 is what we're looking for. Next part of the question asks you to label the zone for alpha emission. Now when we did this, we sort of said that alpha emitters tended to be large nuclei. But then there's a bit of doubt in it, because the textbook seems to suggest that it's large nuclei at this side of the curve. But the mark scheme is quite adamant. It said that you've got to show it's large nuclei, so anything above 60 protons, and it does say on the mark scheme it must be below the stability curve, which sort of agrees with what we said about the fact that if you're losing 2 protons and 2 neutrons, it has a bigger effect on the number of protons than it does on the number of neutrons, because you've got more neutrons in any case. So I would draw the alpha range there. You have to draw the beta minus range. Well, beta minus emitters are the ones that have got neutrons turning into protons. So that must be because they've got too many neutrons. So they lose one, it becomes a proton. So anything there would be the beta minus emitters. And beta plus emission is the opposite. So that's when a proton turns into a neutron. So anything that's got too many protons, not enough neutrons, will have a proton turn into a neutron. So that's going to be below the curve there. And of course, although this question isn't about it, we've also got to remember that things that can give off beta plus might also undergo electron capture. Because it's the same effect of reducing the number of protons, increasing the number of neutrons. So this table is quite straightforward to fill in. We should know what alpha particles are, and therefore what it does to the proton number and the neutron number. Similarly for beta minus beta plus, electron capture, as sort of mentioned in class, that's when a nucleus captures one of the electrons that are in orbit around the atom. So an electron comes into the nucleus and it combines with one of the particles in the nucleus to become a different sort of particle. So I'll leave it to you to work out what an electron can combine with and what it will make when it does that. A couple of other things we've not met before: proton emission and neutron emission. Well, that's just as the name suggests. Proton emission is when a proton gets kicked out, and neutron emission is when a neutron gets kicked out. And it's sort of, by putting these zeros here, it's sort of helping you to understand what's going on there. Question 2. It sort of zooms in on a bit of the n against z curve. It says you've got this element x. Now if x undergoes a beta emission, what's going to happen to its proton number? Does the proton number go up? Does it go down? What happens to the neutron number? Does that go up or does it go down? So beta minus, of course, is when a neutron turns into a proton. So we're going to be gaining 1 extra proton at the expense of losing 1 extra neutron. So the arrow I would draw would be that. Label it A. Neutron emission. So we're always starting at the same place, at the original isotope. Neutron emission, it loses a neutron. So what happens to the number of neutrons? What happens to the number of protons if all it's done is lose a neutron? You can work out where to draw the arrow to show the change in neutron number and proton number. Electron capture. when the nucleus captures one of its electrons, which then combines with something that was already in the nucleus to make something else that stays in the nucleus. What does that do to the number of protons and the number of neutrons? And then you have to give an equation for electron capture by the nucleus, so it's not based on the individual particles but on the whole nucleus. So you started off with the original nucleus plus an electron. What does it give you? What happens to the number of protons? What happens to the number of nucleons? And assuming that something happens to the number of protons, it can't be X anymore, so we have to call it Y, some other unknown element. Question about gamma decay now and energy levels. And remember what we said, that often when alpha decay or beta decay has occurred, you're left with a daughter nucleus that's not in its lowest energy level. We know about energy levels from electrons. Well, the same things apply to a nucleus. Somehow the way that all the protons and neutrons in the nucleus are arranged can be arranged in different ways that have different amounts of energy involved. But just like with atoms and electron levels, you can't have any old amount of energy. There's only certain amounts of energy that are allowed, called energy levels. So this question shows magnesium. It says it's decaying by beta decay to make aluminium, but after the beta decay the aluminium isn't in the ground state. There's two possibilities. You could either have the magnesium losing a beta particle with only a small amount of energy, in which case that leaves the aluminium in a high energy level, which is this one, or the magnesium could decay with a beta particle with more energy. If the beta particle has more energy, that must leave the daughter nucleus in a lower energy level. So the first thing we've got to do is to work out the energy, the maximum energy that the beta particle can have. So we're starting from the magnesium. The beta particle with maximum energy must be the one that leaves the aluminium with the lowest energy, which must be this one. So you can work out from the numbers how much energy must the beta particle have. If it takes you from the energy state up here, where you start, if it takes you to that energy state, what's the energy of the beta particle? It says that the excited aluminium can emit gamma photons, and there are three possible energies. So this is just like what we did when we were doing electron energy levels in Unit 1 last year. The aluminium, after it's formed, can be formed in this energy level or in this energy level. Ultimately it's going to finish up being in the ground state, and there's three different possibilities for the photon energies that can be given out in that situation. You can work them out there. Find the frequency of the most energetic gamma photon emitted. Well, you've just worked out the three photon energies, so whichever one of those has got the most energy, that's the one we're interested in. And we've got to link frequency and energy for a photon. So we do that with a very simple equation that we used in Unit 2, and it's on your data sheet. Equation linking energy and frequency for a photon. State and explain two precautions taken when working with a sample of magnesium-27 in a school laboratory. And it's worth noting that they haven't just given any old element there, it's the one that you've been working on. This one here that emits beta and gamma radiation. So you've got to think of two precautions to be taken when dealing with beta and gamma sources in a school lab. I'm not going to do that for you, find it yourself. Then discuss which of the two types of radiation, beta minus or gamma, emitted from this sample would be the more hazardous. So you've got to use your knowledge of the difference between beta radiation and gamma radiation and think about why they behave differently and relate it to how their behaviour could affect the cells in your body, because that's where the hazard comes in. Here we're told that this lead-210 isotope is unstable and decays in 3 stages through alpha and beta emissions to give a different lead nuclide. And we're asked to show the decay route, in other words, which order the alpha and the beta decays occur in. It does say one possible decay route, because I suppose it's possible that different orders of the particles could happen. But hopefully we can spot straight away that every time we've got an alpha decay, the number of protons is going down by 2. Every time we've got a beta decay, the number of protons goes up by 1. So because we want to end up having the same number of protons as we start, that must be 1 alpha decay followed by 2 beta decays. Well, that's one way of doing it. You could have them in a different order. You could have two betas followed by an alpha, or a beta followed by an alpha followed by a beta. If we show the alpha decay happening first, when an alpha particle is emitted, you're losing 2 protons and 2 neutrons. When we check this graph shows neutrons on the y-axis, protons on the x-axis. So to lose 2 protons is to go across to the left by 2, to lose 2 neutrons is to go down by 2. So that's the alpha decay. When you get a beta decay, a neutron is turned into a proton. So for each beta decay you've got 1 fewer neutron and 1 extra proton, so that would be the neutrons going down by 1, protons going up by 1. That's for the first beta decay, and that will show the second beta decay. It says to label them, so alpha, beta, beta. This copper nuclide can decay by positron emission or by electron capture to form a nuclide of nickel. So 2 equations. So positron emission, that must mean you just start off just with the nucleus, which then breaks up into 2 or more parts. So emitting a positron, so whatever the daughter nucleus is, plus the positron. So if we're losing a positron, what's happening inside the nucleus? Something with positive charge has come out, so that must mean that one of the protons has stopped being a proton because it stopped having positive charge. If it stopped being a proton, what can it become? It's got to become a neutron. So the number of protons has gone down, but the nucleon number must stay the same because a proton's become a neutron. And we're told that we're making nickel. So that balances the protons and the neutrons and the charge, but there is still something missing. We're creating a lepton that wasn't there before. Well, no, we're actually creating an antilepton that wasn't there before, so we've got to have a lepton created as well. Electron capture, so where the nucleus captures an electron, so to begin with we've got the nucleus and we've got an electron. They're both there to start with, and then they join together. And when they join together, the electron combines with one of the protons, turning it into a neutron. So instead of having 29 protons, we're down to 28, which we know is nickel. Protons become a neutron, so you've still got a total of 64 protons and neutrons. Trouble is, we've just had a lepton disappearing. The electron was there and now it's gone. So we've got to have leptons conserved, so we must get a neutrino to make up for the loss of the electron. Part C, the sort of written answer that people like missing out and just think, oh, I'd be able to do that in the exam, and then never practice and so do badly on in exams. So we can investigate the nucleus by bombarding with radiation or particles. Name one type of radiation or particle that may be used. Well, hopefully you're aware that Rutherford used alpha particles, bombarded them at the nucleus. So I'd be inclined to use that as my example. Describe the main physical principle of the scattering process. What does it mean by that? Well, when the alpha particles are approaching the nucleus, we know they get repelled, don't we? That's the whole idea behind it. The ones that come close get repelled. Most of them, of course, go straight through the foil because they don't get close, but the ones that get close get repelled. So what's the physics behind them being repelled? Well, hopefully you realise it's positive alpha particles being repelled by a positive nucleus, so it's electrostatic repulsion, electrostatic forces. That's the principle behind the scattering. And what information do we gather from the scattering? Well, it was in this experiment that Rutherford realised that most of the mass of an atom is concentrated in the nucleus. By doing the calculations on the forces and things, and the energies, we're able to estimate the size of the nucleus, because it doesn't give us the actual radius of the nucleus, it gives us an upper estimate. We get a value and we know the nucleus must be smaller than this answer, so it gives us an upper estimate of the nuclear radius, or upper limit.